two equations, two unknowns tonight. Now, it's probably unnecessary to write this down, but x and y are both complex numbers. The solutions are going to be complex numbers. And it's pretty evident that that's going to be the case just because you have the complex constants here, complex number constants on the right-hand side. So we'll write down a C like this. I guess some people make it look crazy like that, right? Okay. But anyway, these are supposed to be the complex numbers. All right, now I'm not going to go through every last computation with you, but I just want to talk about the algebraic structure, and then I'll try to give a kind of a guideline on the computations. We're given that x cubed plus y cubed is equal to this complex number, then x plus y is equal to this complex number. And we're supposed to evaluate the product xy, not find x and y individually. And these kind of problems are very prevalent these days, where you don't actually find the solutions, but you find some combination, some algebraic combination, multiplication, division, subtraction, of the two solutions in this case, x and y. Now, x plus y raised to the third power, this is very well known, a binomial expansion. But the part that really does the most work here and really gets to the crux of what we're trying to do is here, these two middle terms here have a common factor of 3xy, okay? And then look what happens. You have an x plus y here, which is an actual given, okay? So x plus y is right here in this factorization, okay? And so that sets everything up very nicely because on the very next line, we just make substitutions. X plus y is 6 plus 8i, so you put it right there, okay? And then also x cubed plus y cubed is equal to minus 282 plus 124i, and you put it at the front here, okay? See, that would be this part, x cubed, y cubed is here, but you put it out front just for the sake of representing it here. And notice at this point we have one equation, one unknown, okay? This is just one equation and one unknown, and the unknown is just what we're looking for, the product xy, okay? Now the rest of this, folks, this piece right here, again, I didn't show all the details here, but all I did was just use this binomial cubed result, which is really what this first statement is right here. Just after you do the binomial cubed, and again, I dispensed of all those steps. There's no need to show you. All you guys can do that. It's just a matter of remembering that I squared is equal to -1, okay? I squared equals -1, right? That's just the defining constant of the complex numbers, the imaginary part, I think some people call it. Some people like to call it I is equal to the square root of -1. But in this case, it's just important to know that I squared is equal to -1. When you expand this out, you'll get this value right here, this complex value right here, okay? And then also when you do the work here, when you substitute, when you multiply this out right here, you see, well, I just substituted it directly in there, okay? And at this point, you can algebraically isolate x, y, all right, which is what I did right here. Okay, folks? And again, some of the computations are omitted, quite a few of them, in fact, but the overall algebraic structure is all that really counts here. Now, this is kind of in a sense, you're already done with a problem, except you haven't written it as a complex number yet. It turns out 6 is a common factor to all these numbers. If you divide this by 6, you get this. Divide this by 6, you get this. And so on. And think of it as dividing the numerator and the denominator by 6, which is tantamount to multiplying the complex fraction by 1. Okay? Now, so at this stage, let's see what we got going on. So I wrote this here just so I wouldn't have to write as much. Y'all, a very, very common trick is to multiply through by the complex conjugate. It takes advantage of the difference of two squares. So we would multiply top and bottom by 3 minus 4i. Okay. And that's where the definition of I squared of being -1 is pretty important. So right here, 3 minus 4i. And again, a lot of mathematics sometimes just multiplying through by a cleverly disguised version of 1, right? So notice this is just the same thing over itself. It's equal to 1. But you have this form a plus b times a minus b, okay? And so what you end up with, and I'll just write out the, I'm not going to do every last bit of it. I'll tell you what the result is, and you guys can verify if you want. but you would have minus 109. Okay, plus 38i. 38i. Okay, let me wrap that in parentheses. Okay, times 3 minus 4i upstairs. Okay, I'm just recopying what I did. Now downstairs here, at the bottom of all of this, see, you're just going to have 25. Now that's kind of the whole justification for multiplying through by the conjugate, because what happens here, 3 times 3 is 9, right? Okay, but 4i times 4i is 16i squared, which is minus 16, but this minus sign makes it plus 16. So you see how this is equal to this is equal to, I'll just write it here, this just the denominator here is equal to 9 plus 16. Okay, which is the result of this product 3 plus 4i times 3 minus 4i. Okay, now again, y'all, just to save space here, and I don't think you really are that interested in seeing it, this ends up being, and this is going to be the answer here, this ends up being 7 minus 7 plus 22i, I believe. Let me check. I multiplied it out. Yeah, minus 7 plus 22i. Which is the final answer without knowing what the zeros are, or the roots of the original equation. So that's our answer, folks. Minus 7 plus 22i is the solution. And like I say, I think the coolest part of this was just the funnest part. The rest of what I just showed you is a lot of computations, but just writing this down, and then noticing you could factor 3xy to both terms, and then you're left with a given. You see x plus y here is given. That's very cool. All right. And so it goes in 2 different places, and also the x cubed plus the y cubed. The x cubed here and the y cubed here is given, you see. So very neat stuff, I think. You could do what they call elementary symmetric polynomials on this. It's not necessary. You're better off just doing it directly, I think, in my humble opinion. And again, I hope you like that. I thought it was pretty slick.